hardware emulation. Hardware emulation for a functional verification of K5. The K5 TM microprocessor is a 4 million transistors superscalar x86 microprocessor. The K5 TM microprocessor is an AMD original design, verifying compatible with the existing x86 architecture, and software is crucial to its success in the marketplace. The x86 architecture has been constantly evolving over several years without any published specification. The primary mechanism for functional design verification of an x86 processor is simulation. The ability to execute a good sample set of the x86 software based on a model of the processor architecture before tape-out is the key to achieving a very high confidence fuzz silicon. The Quickturn hardware emulation system allows us to map a model of a design onto hardware resources and execute it at a higher speed. In this paper, we present the emulation technology that was jointly developed for the K5 and applied successfully to meet our functional verification goal. And the introduction. The fastest hardware accelerators commercially available today can simulate a full gate level model of the K5 TM microprocessor in the low 100 Hz range. At this simulation speed, building an operation speed like Microsoft Windows and then starting an application like Word or Excel is practically impossible. One and two had described the benefits and the value of a hardware emulation-based verification methodology. The hardware emulator map on a gate-level model of design into a field programmable gate-level arrays FPGA on the emulation system. This model can be executed in a high 100 kHz range, giving us 3 to 6 orders of magnitude improvement model execution performance. This speed combined with the very high instructions and execution rate per clock cycle (IPC) of the 4-issue superscalar K5 TM core allows us to interface the emulator directly onto real hardware like a simple PC and execute the x68 application in minutes, instead of say days and months in a simulator. 2. Emulation hardware. The K5 TM emulation system is used to generations of emulation hardware from Quickturn design system. The initial system was the MARS TM IP2500, Figure 1. The system was comprised of the 5 IP500 chassis interconnected together, with approximately 400 cables. Each IP500 chassis has a 5 logic board LBM with a rated capacity of 100 gates each and a total system capacity of up to 2.5 million gates. However, the actual gate densities vary depending on the topology and regularity of the logic structures being mapped onto a board. LBM and LBM interconnections are all unidirectional. 3 unidirectional pins are required to model every bidirectional bit. A configuration memory module (CMM) is used for modeling array structure. The target system, a generic DX86 PC system running in the megahertz range with a custom interface board to a buffer transaction to the slower emulator side. Saturn TM, the current generation emulation system from Quickturn, utilized the higher capacity FPGAs and better interconnect technology. The entire K5 design now in a single Saturn TM chassis with 11 logic boards. 3. Design partitioning. The K5 microprocessor has a 4-issue superscalar process core with 2 ALUs, and a branch unit, and a load store unit, and a floating point adder, floating point multiplier, and floating point shifter. There are 16 shared 42-bit bidirectional buses that connect between all of the above function units. All these buses feed into the multi-port register file and reorder buffer. Additionally, there are wide buses from the instruction and data caches feeding the instruction, decodes block, and the load store sections. Partitioning the K5 into 25 LBMs in such a way as not to overflow LBM and FPGA pin limits proved to be a major challenge. Spatial modeling and identification of all tristate signals is also necessary. The multi-port register file and reorder buffer had to be modeled along right port boundaries with multiplication of storage bits. Tri-statable wired low-OR structures had to be converted to an input static OR gate with the tri-state buffers on the OR gate output to reduce the number of the signals traversing LBMs. The initial bring-up time of the K5 hardware emulation system was dominated by this partitioning and mapping iteration to meet emulator constraints. The Saturn emulation system, with its higher logic and the pin capacity, reduced the partitioning problems to a large extent. 4. Design mapping. Both generations of the Quickturn emulation system use the Xilinx FPGA as basic building blocks for mapping logic. The entire microprocessor has to be mapped into a set of basic primitives like flip-flops, muxes, and 4 input combinational functions that are implemented in the Xilinx FPGA. For example, there is no direct support for thousands of complex switch-level circuit implemented in a full custom processor like the K5 microprocessor, so a gate-level emulation model that is the functionality equivalent to a real transistor-level implementation of the design has to be generated. Quickturn software uses many compilers that map memory arrays to FPGA directory. This requires that internal memory arrays to be presented as black boxes with read and write enablers, address and data buses, simplified version of the I/O pads, clock generators, bus drivers, and receivers built again, level 4 emulation. All delay-dependent logic, like self-timed structures, are removed from the emulation model and replaced with a functional equivalent. External timing signals are used. Maintaining the consistency between this additional emulation view and the real representation of the design was expensive and required dedicated emulation model build resources. The initial K5TM emulation model was verified by simulating the K5 test based on a hardware accelerator. Gate switch equivalent checker were later used to maintain this model. Thousands of FPGAs are involved in mapping K5 class design on emulator. The partitioning the placement of a cone of the conventional logic onto FPGAs that are physically far apart, and routing signals between these FPGAs using long cables makes it necessary to handle very large delays and signal skews on the emulation system. The K5 is latch-based design using two-phase, the non-overlapping clocks. There is significant emphasis during the development phase to make the timing analysis of the K5 emulation model as simple as possible. A complete list of all gated clock location is provided in advance to make sure that the setup violation on the conditional signal to a gated clock can be handled. By varying the non-overlapping between the phases and the duty cycle of the phases, hold time and critical path issues were identified and resolved. Mapping the emulation view of the K5 onto the Quickturn hardware involved 4 major steps. The first step is model build. where an emulation view of the design is generation. The second step is partitioning, where the design is partitioned into LBMs in such a way as to meet the logic and P constraint of each LBM. This is followed by compilation, where the logic partition assigned to each LBM is flattened, checked for the connectivity and the timing consistency, and further partitions into smaller logic clusters, each of which can be fit into a single Xilinx FPGA. This involves steps like placement and routing between FPGAs. The final step is linking, where all the LBMs are linked to the final interconnection are completed. At this point of the design is ready to download it onto the emulator and test it. The process of starting from a netlist and generating the emulator program files is very compute and disk intensive. The large number of LBMs and the thousands of FPGAs involved allows us to parallelize this task. We used several workstations to compile the LBMs in parallel. The FPGA place and routing step used hundreds of the networked workstations to generate the required program files for FPGAs in the emulation system. Emulator operation mode. The K5TM simulation environment models a simple x86 PC system with external memory, AEXTMEM, memory controller, EXTCTL, and the event generators and monitors that mimic the bus master and the other devices on a PC. Test suites are developed in an x86 assembly language and assembled, linked and loaded in the EXTMEM. EXTMEM is mapped onto the CMM and can be read and written without disturbing the rest of the design. This mode is referred to as a simulation mode. The simulation sim mode of the operation on the emulation hardware allows us to use the emulator as a very fast simulator. An external monitor board is used to drive the clock, reset the system, and display the pass or fail status of the test on a system-built monitor board. This mode is very useful during the initial validation phase to verify the functionality of the K-sim emulation model through the full regulation of the K5TM test suite. The debugware, a combination tester and a logic analyzer that is part of the emulation system, is used to probe the key signals and read back most internet nets for debugging failures. The readback operation utilizes scan architecture to retrieve the internal state of the desired net at the specified times. In the in-circuit emulation eyes, both the pin of the K5TM Pro microprocessor are brought out to the x86 PC target system. This is the in-circuit mode used to execute the key x86 application. An in-circuit buffering mechanism, Figure 3, is implemented to facilitate the switching between the ICE and SIM modes, ICE and SIM modes, without disturbing the design loaded onto the emulator. This reduced the need for maintaining two different emulation views of the design, one of each mode of operation. Incrementally changes to the design can be made at different levels. For small changes localized to a single LBM, and the partitioned database for the specific LBM is carefully edited, and the affected FPGAs are repartitioned and compiled. This is accomplished in a few minutes. For more complex changes affecting the multiple LBMs, and the LBM database needs to be edited and repartitioned. This level of the incremented changes takes from a few hours to a day, depending on the number of the LBMs affected. Number 6. K5 hardware emulation cycles. During the course of the K5 project, the hardware emulation has been called upon to perform a variety of tasks. The K5 hardware emulation project cycle could be broken down to the key phases. Methodology phase. This phase involved the plan, design, and initial experiment that results in hardware emulation methodology. Compilation and partitioning of the entire K5 design was achieved by working with smaller blocks and getting a better estimate for the optimal partition of the design. The close interaction of the Quickturn R&D team and the AMD engineers was critical to the success of this phase. Once the first K5 database was successfully compiled, the methodology and the design is initially verified with very small test cases running for a few hundred clock cycles. A number of hardware and software issues were resolved before these small test cases were successfully executed. Validation phase. The goal of this phase is to verify the K5 process in emulation with the verification of validation suits. This phase is confidence builder in an emulation methodology and system. Experiments are performed to arrive at the optimal parameters for operating the emulator. The hardware is operated in primarily the SIM mode. In parallel, the emulation interface board and a target system is manufactured and tested at the emulation frequencies. The system's verification phase. This is the most critical phase of the project cycle where we execute the x86 applications. Initially simple diagnostic tests that verify the hardware interface are run to test the ICE mode operation. These diagnostics are run from the ROM on the motherboard. The next step is to run billions of cycles of real x86 application software to verify key compatibility and functionality issues. This level of verification and testing can be achieved before the first silicon solely due to the execution speed of the hardware emulation. In this phase, the hardware emulator is the primary failure detection mechanism, ably supported by extensive random test generation in simulation. The silicon test support phase. In this phase, the primary function of the hardware emulator is to reproduce and isolate the failures found in using silicon validation board. The emulator is more of a failure isolation and fixed verification platform. Incrementally changes made in the design are verified in the emulation before committing these fixes to the design database. The system's regulation phase. The primary task of hardware emulation in this phase is the system regulation for verifying every revision of the design prior to tape-out. The regulation and debug process start with executing a number of 16-bit and 32-bit x86 applications. A harsh environment is created with other bus masters and an event generator plugged into the target system for stressing the design. The 7. Discussion. The design and development cost of successful emulation are significant. Large emulators are expensive and thus limited resources. There is a high startup cost of in full custom design due to the modeling and partitioning constraint enforced. A dedicated team of engineers is often necessary to effectively compile and debugging the design of the emulator. When compared to simulators, the time to debug and measured as the time it takes to be productively debugging on the emulator from an initial netlist is measured in hours instead of minutes. Debugging productivity is also affected due to the cost of adding probes to observe additional signals and iterating in this process to isolate failures. However, compared to debugging silicon, the emulator provides a friendlier and more productive environment for isolating failures and verifying bug fixes. It is possible to try out different options for tuning architecture performance or bug fixes before deciding on an optimal fix. The emulation compilation time is insignificant compared to silicon fabrication, and the system development time is very attractive. Speed and the ability to directly interface with the real hardware are the two major differentiating factors between emulators and traditional simulator. The very high emulation speeds give us the ability to debug x86 application on a model of design well before first silicon with a simulator-like debugging environment. Successfully executing key operating system and applications before tape-out is a huge confidence builder and positions the design for silicon validation on hundreds of PC systems as well as the first silicon is available. This gives us the ability to quickly go after those bugs that are difficult to find. If we relied solely on the directed test and random test generators, it is possible to miss that one bug which prevents us from learning key application on the first silicon, thus delaying the silicon validation and hence final production. The K5TM emulation system was used to debug and verify several key 16-bit and 32-bit x86 applications. Several bugs were identified and fixed in this process. Emulation was incrementally in achieving the very functional first silicon on the K5TM microprocessor. 8. Conclusion. Hardware emulation of design size and complexity of K5 microprocessor has proved challenging. A large number of operating systems, including Windows 3.1 and Windows NT and 95 and OS 2, and Linux and their application, have been demonstrated on the emulator. Despite a rigorous directed and test generation flow and an extensive random test generated flow, a few key bugs have been found and fixed using the emulator. The K5TM hardware emulation system has been extremely valuable in getting the first version of the K5 microprocessor into production. In the future, with a higher emulation speed, we expect the emulator to be a very useful tool for tuning architecture performance and against a wide range of applications and benchmarks. 9. Acknowledgement. The success of the K5 hardware emulation is attributed to the contribution of Elango Raja Gopal. The people's name, Yukchong-won, and others. The authors acknowledge the support extended by the Quickturn R&D and expert user groups. Okay, thank you for your time. Okay, figure 1 is MIRS3 emulator building blocks. Figure 2 is K5 emulation hardware. Figure 3 is buffering scheme for in-circuit emulation. Okay, thank you for your time. And I read the paper, Hardware Emulation for Functional Verification of K5. Thank you, everyone. See you next time.